Right, I'm recording. I'm assuming the team thing's gonna. Is it still broadcasting on the time?
Yeah.
So I'm waving my hand.
Yeah, I can see that.
Right, okay. Right, okay. Right, this first question then. Easy meat. Easy meat. So I thought. Right, so I've given you a blob of memory, and now I filled in the current state of the registers on purpose to try and throw you, which I think threw you too much. Some of you. The only one that matters is which. Which register is the only one that matters before we start the fetch execute cycle? PC. That's the only one. All the others are going to update potentially, aren't they? So the only one that controls it. So you didn't need to know where we were. We just follow the state of the PC. So we just do the first bit. So we transfer the PC to the MAR. So what I expected to see was 3000 went in to the memory address register. You should be able to see that on your screen, Dan. Is it coming up? On the broadcast, is it? Is it? How laggy is it? Was it?
What, joining?
Yeah.
It's...
Are you even joining?
I am. It's just wearing away.
Do it in Edge. Do it in Edge. Oh, you doing it on your laptop?
Yeah. It's don't worry, we're on.
Right, this is a slick presentation, isn't it? Right, okay, so that's the first page of the fetch set. Now I said here, summarise what's happening. Thank you.
Thank you.
You don't need, you can get it live. Summarise what's happening. So you need, I don't want you to generalise. A few people obviously didn't know what to do on the question and told me what the fetch execute cycle was. I know what the fetch execute cycle is. I wanted to know how it was performed with this instruction. Okay, right, so the first step is that PC to MAR. So I'll just fill that in. The next step is to do a read, isn't it? So we read from that memory location. So we look at our contents of memory. What was in there was LDA bracket 299. Now obviously that's just binary in reality, but we're abstracting it a little bit. That arrives at the MDR. So I expected to see LDA 2999 in the MDR. Because it is the initial fetch phase, we assume that's an instruction. So we take a copy of that and transfer to the current instruction register. Okay, we then do the decode. And remember, as we decode, that's when we do the increment of the PC. So we're only writing down as things change. Okay, so the PC is updated. So I can't execute yet because I haven't got my data, but we've decoded that instruction and we can see it's indirect addressing. So that means that that address is the address where I'm going to find something else. So if I want to access that address, I'm going to put it, the operand, in the memory address register, because that's how we access memory locations. Okay, we then do another, so the control unit goes, oh, do another fetch, and it will arrive at the MDR. So at the MDR will be the contents of 299. These will always be confusing. So I put 3002. That's what arrived. But because this was indirect addressing, the control unit then goes, right, okay, so I've just gone and got the address of the data. That's what indirect means. So I want to actually put that address back in the memory address register because that is where my actual data for the load instruction is. So the control unit goes, right, okay, so I've selected this new location, I now need to read. So I read the data at location 3002. So 15 arrives at the memory data register. At this point, the control unit goes, right, I've now got the data I require to execute this instruction. So it goes into execute phase. And the execute phase is load the value to the accumulator. So we end up with 15 in the accumulator. What's the very last phase of the fetch execute cycle?
You copy the PC to the ML and then...
No. That's the next fetch execute. What's the last phase of fetch execute? Yeah, check for interrupts. Check for interrupts. But obviously that doesn't affect anything in this example. That is the end of the execution of that instruction. So the way that I sorted the marks out for this is that if the PC and MAR column were correct, you may have carried on and executed the other ones, but I didn't ask you to do that. Okay. I just wanted that one. So the summary, if you ever get asked to explain how an instruction executes, make sure you tie it. So you're going to say the PC goes to the MAR, so 3000's in the MAR, then do the read, decode increment. It's an indirect, so we need to put an address in the memory address register, read, use that address in the address register, and you can see that that's what's happened during the steps. Okay? Don't worry what other values were in the registers. The thing that people did wrong is people started just, I don't know why. They went, all right, let's put 3002 in there, let's put a 15 in there. The whole point of the current instruction register is to keep a copy of the instruction that we're in the middle of sorting out the execution for. It shouldn't ever have anything except a sequence of instructions that we've executed. Anyone got any questions about that? How do I see the chat for this? So, can someone just put something in the chat? Just to see if it pops up. Oh, it is there. Thank you. I'll see you later.
Yeah.
Right, okay, so that does it work if I reply back? That come up?
Yeah.
Right. I wish it wouldn't do all that, like, boxes popping up junk. But at least that's not on the OBS bit. Right, so that does come up. Right, okay, so is that, you've just got to be logical about executing. Now, bearing in mind that they may do weird things, and we'll come on and we'll look at some of those when we recap Little Man Computer later on. Okay? But yet, straightforward. The fetch execute cycle stuff is bread and butter. Right, the binary search stuff, and then in search, you did it quite well, and you all went in a structured way. There was only, for most people, there was only a few bits they didn't talk about. But remember, it's factual stuff, so talk about, like we do for all algorithms, how they start, what their process is, and how they end. So always give something like that. If you're talking about a couple of algorithms or describing how an algorithm works, always. So like with linear search, you've always got to say, it starts with the first item, does a comparison. If it's the one it wants, fine, we stop. If it isn't, it increments. Because that's the key thing about linear search, isn't it? It's an incremental system. We just move to the next index. And we keep doing that until we either find the item or we get to the end of the list. Okay, so you can start off with a factual explanation. With binary search, you say, you all thankfully said it has to be sorted. That's great, because it was a prerequisite. And then most of you then did go on to say, yeah, and that's one of the benefits of linear search, that you don't have to do a sort. But you need to explain the process again. So looking for the middle value, checking to see if that item is the one we want. If it isn't, it's a little bit more complicated, isn't it? If it's bigger than the one we want, we ignore the items to the right and we look at the left-hand side of the remaining list. And then find the middle, and we go through that process until we've exhausted the list. Now you can say that the left and right pointers become swapped, because that's one of the conditions, isn't it, that does that detection. Once you've done that technical, so you'll get quite a few marks for the technicals, you've then got to do the chatting about them both, haven't you, and doing the trade-offs, and I did say talk about edge cases. So most of you did say that linear search, the best one is it's the first item, and some of you did say, oh, with binary search, if it's the middle item, that's going to be your quick stop. But you also said, which was really good, was that because we have to sort it, that might not actually make it slower. because it just depends on how many data items. If you pair, let's say for instance, for the sorts that we do, if you pair merge sort with binary search, that actually might still be quicker than linear search once you get to a certain number of data items. Okay? We know that it's a linear increase for linear search, which is why it's called linear search. But the binary one, because it's logarithmic, and always, they will say in the exam, on paper 1, you don't have to mention big O because it's a paper 2 topic, but they will give you credit. So I just think you should get into the habit of talking about big O to do with the algorithms anyway. All right, but yeah, so you've got that caveat. It might actually still be better to search, but it depends on what data you've got. And a few of you did say that if you're keep adding to this data set, if you then have to keep sorting it, then that actually could start to become a thing, couldn't it? You could, if you want to go super technical, you could talk about cache. That if the linear search data is completely in the CPU cache, then actually that's going to be incredibly quick, because that operates about 10 times faster. And there is like massive debates over array-based methods now because of cache. So you can mention that. You're getting towards like outside the scope of the question and the scope of the course, but it is a big debate on how to write algorithms that make use of the cache. Yeah, so there were a few good things that people said. That was, if you've got a linked list, linear search is your only option. So that was a really good deep. And remember, the marking on this is that you show a real good rounding. If you get into those high band marks, you're showing a deep understanding of the topics. So if you talk about linked lists, and I think someone said, there was a few people said linked lists. Yeah, you don't know where the end is, you only know where the start is, so it has to be a linear search, unless you organize it into a tree structure and then you can binary search. Okay, so there is tons and tons and tons of things you could have said about these. And it is basics of, if someone asks you to state the features of a linear search, that's where you're going from. So it's all the things you know about linear search, all the things you know about how binary search works, and then you're just clashing them together and discussing it. So it is important to, in your summary, to say that if the data set's small, there is so much work involved in just finding the middle, doing the comparisons, doing the discarding, changing the pointers for left and right, compared to what linear search does, which is just add one, then you've got that massive benefit. But only with a certain list. And at the end of the day, you remember big O is just an estimate, isn't it? It's an approximation of time taken. So you would need to do experiments and conduct experiments with your data in order to make sense of which one you would use. In the same way that for your projects, there may be 3 or 4 different ways of generating a maze or doing your navigation, and it might be that until you do an experiment and do some runs and times and things, that you don't know which is going to be more appropriate. But yeah, of all of the questions, that was the one that everyone answered consistently. So we are getting better at those. We still got to work on it. The hardest bit is repeating yourself. There was a bit of repetition. I think that's really hard to do. Sometimes if you're going to do a comparison, is it better to like explain how they work and compare them at that point, because you start getting into more complicated things and it gets a bit jumbly? Or do you just state how they work and then move on to the comparison and try not to repeat yourself? It's the tricky bit. But yeah, it was generally well answered. It just needed to be fully fleshed on that one. Right, okay. Any other things about that question before I move on to the floating point question? Right, floating point. Oh dear. Right, you have got to nail this down. This is easy marks in the exam. If there's a binary question on there, you are doing it first, you're getting it out of the way, you're getting loads of marks. Show you working, you will always get marks for working. So whenever we're writing down these numbers, we go fixed point binary first. So I'm always going to start, I'm going to turn it back into pen mode, it might work better. we're always going to start by putting a binary point, and then I'm just going to like say, right, I've got to write down 4, but it's positive 4. So I've got to make sure I've got enough columns so that I can put a sign bit in. I always put my sign bit in. So I'm going to do that and put a sign bit in of 0. Then I'm going to write down 4. Now my fraction bit, I need a half and a quarter to put my 7/5 in. So that's my start, but that isn't all my working out yet. I've now got to do the normalisation bit. And remember, normalised form is where the sign bit is followed by a detail bit. Did that just flicker?
Yeah.
I don't know why. Probably because we're all trying to do team streaming at the minute, and it's killing the network. Right, so when we got a positive number, the first bit of detail is going to be a 1. When we got a negative number, the sign bit is 1, and the first bit of detail is actually a 0, because that's how you read. It's like an inverse form, 2's complement. So we're looking for the last sign bit before a detail number. So I start here, and I do keep saying this, but it is important to show which direction you've gone. So always when you're doing the loop, 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 you end it with an arrow so they can see. If you don't do that, how do they know that you started there with the binary point rather than there? Right, so I will get a mark for that. All right, or if I followed through and did that working. And then all I've got to do is write down in the format I was given. So I was given 6 bits from Mantissa. So I'm going to write 0. I don't have to put the point because that's just an implied point, but I'm going to put it for readability's sake. So I go 2 bits, 3, 4, 5, 6. Luckily I can precisely hold this value. If I'd have asked you to do a 16th, we'd have been stuck. And then I've got the exponent. So the other thing I'm going to do here, I'm going to say 3. Now we need to know whether it's negative or positive. Okay, so I know its magnitude is 3, but the way to do this is if I started with a number bigger than 1, it's always going to get shrunk when I normalise it. Because really that's the half column there, isn't it? So it's become less than 1. So when I read it back, I need to make it bigger. So that bigger means positive. So I need to write down +3. So I've got 4 bits for this. Now I didn't say in the question, but assume it's 2's complement. They should say in the question. Okay. So I just write down 3. So I get a mark for that and a mark for that. And I got a mark for me working. The working's got to be the right working. If I screw up writing it down, at least I've got a mark. Okay. Second one, I'll do it a bit quicker, same process. So I'll put my binary point in. I need to do +3, so I only need 3 column headings this time. So I'll put me positive in, write down 3, and a 1 1/4. So don't make the daft mistake of just putting a 1 down. It is actually a quarter. Okay, so that's my starting point. I need to normalise it, so I'm going to move it 1, 2 places. So I'm just going to write down the number 2. So I remind myself. So I'm just trying to follow the process through. Right, I can now put down my mantissa. So I've got 0.1101. Oh, I need an extra bit. Don't ever just put 5 bits if they've requested 6. You've got to pad it with a 0. It's wrong if you don't do that. I then need to write down my exponent. Again, this was a number that was bigger than 1 to start with, so we'll always have to make it positive. So it's going to be +2. And the other thing I would recommend you doing is just saying mantissa, just in case. I know what some of you like. I don't, you put 0s and 1s all over here and there, and I'm just going to label it just in case the person reading this is not very comfortable with floating point and they don't read it properly, or the mark scheme has it the opposite way around or something weird. Okay, so that was like easy meat. That was. And then we had this to do, working out. Right, so your first thing, whenever you get anything like this, you can do the subtraction route and do it long subtraction, but I don't recommend it. So we're actually going to put 32.5 minus 4.75, but we're going to say, well, that's the equivalent of 3 point, I got ahead of myself there, plus minus 4.75. So I'm demonstrating to the examiner that I'm reformatting, I'm rearranging this equation so I can use the method that the CPU will use. So I'm going to find the 2's complement of 4.75. Now I've already worked out 4.75, but to save you some time, if you do have to do this in the exam, we're going to add up the unnormalized versions. So let's take the unnormalized versions of these numbers. So I've got the 3.25, so I'm going to write down 3.25, which unnormalized was that, because we want the binary points to line up, otherwise it's not going to add up. It'd be like adding 1,000 to 10 and randomly putting the 10 anywhere under the columns. So I'm going to write down that. So I'm going to write next to it 3.25. I don't want anyone, this was a bit of a messy question for quite a few people. There was binary numbers everywhere. And you're reading it and you're thinking, really? Really? What about, I'm following this, I need a glyph map to follow it, a Rosetta Stone or something? Right, so I've written down my 3.25, waiting. Now I'm going to take my 4.75, so if I'm going to look back up to what I had, so that was 0, 1, 0, 0, what was the rest of it? 111. 0.11. Now I know that that's 4.75, but I'm going to do 2's complement on it now. So I'm going to say 2c, I'm annotating it. So the examiner knows that I'm doing something rational and not just randomly writing some binary patterns. So I'm just going to flip. So I'm going to do flip, 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 flip. Last one, keep it as a 1, remember, and then everything else just writes down. So that is now minus 4.75. That's what I'm going to add. I know I saw a few people, they did the flip here, and then they had to cross through the other one, and you're just making it, you're asking for mistakes. Do it just at the side, but say what you were doing. Right, so I've got 10.110, and then I end up with these extras. So I need to make sure I sign extend the 3.25. So I've got match, just for sanity's sake. And then I can add them up. And I've got to be dead careful. A few people screwed this question up, not because they couldn't do it, because they didn't do the add and carries properly, which is like the bonehead bit. Right, 1 and 1 is 0, carry 1. 0, 0 and 1 is 1. Put my binary point in. 1 and 1 is 0, carry 1. 1, 1 and 1, and a few people put 0, carry 1 here, which is like, oh, what did you do that for? It's 1, carry 1. Then we ended up with 0, 0 and 1 is 1 and 1. Now we expected the answer to be negative. We know it's minus 1.25. So that is encouraging, that the sign bit is 1. It asked me to leave it in normalized floating point. I don't have to convert it. Okay? It doesn't look like minus 1.25 because it's 2's complement. I could check. I could do that at the side and check it if I wanted to, but I'm not going to bother, but I've got to normalize it. So looking at this, we're looking for just one sign bit. So we're going to move it to there. Okay, so we get like a smiley face with a nose. I always like that. Because I'm stupid. You do as well, Luke. Right, so now these are discarded details. They're wasting precision, so that's why we're normalizing, remember. So we're going to write down 1, 0, 1, 0. We've got a couple of bits we need to fill in, so we're going to pad it out with the 2 zeros. We moved it 1. We've made the number bigger, so it's going to be an exponent of positive 1. And again, I'm just going to put mantissa, and I'm just going to put exponent. Okay. But look how I presented it. Now, I'm not the neatest person in the world, okay? I'm the world's worst speller and I am Mr. Not Neat. But I have presented that with thoughts about my old maths teacher ringing in my ear, like giving me 0 marks for a question that I got completely right because I didn't double underline the answer with a ruler. Oh, but she was teaching us a lesson. And the lesson was presentation matters. All the binary questions are gift questions. Right, okay, the last one, the doozy question, which I think I was actually quite proud of you all. You won't get anything harder algorithm-wise to follow. So we got a Dijkstra. The only thing was that the odd person just screwed up and started doing a bit of Dijkstra rather than A* notation. Remember with Dijkstra, we put all the nodes into the set, the open set, and mark them all as costing infinity apart from the start node, which we must set as 0. So a few people did that, and it was like, no, this is A*, it doesn't work that way. We put the start node in. So the best way of writing this, and I always do it alphabetically, just for my own sanity's sake, I just write down all the nodes alphabetically. I'm trying to make it as clear as possible to the reader, who I know is not going to follow this. Okay, so I'm making it as clear as possible. I'm going to use an X notation to say that's closed and not available to be viewed anymore. So I need to keep track of G. The G cost may change, so I need to make sure I leave enough space between the next column so that I can show my changing of the data set. Same with the H cost. Well, the H cost shouldn't change, should it? That's the heuristic, the square numbered bits. So I can cramp up a little bit. The F cost will change because that's G plus H. And again, just for your own sanity, you could write that for yourself so you just remember. Okay, and then the other thing, so the F cost might change, so I'll leave a little bit of a gap. And then we've got our root, the parent. Who did I leave to get to this node? Okay, right, so I'm going to put in, and I can write all this down. I'm going to write all those heuristics down for these things. So A had a heuristic cost, and remember the heuristic is an estimate of how far to the goal. So 16 for A, B was 5, C was 9, D was 0, because that's the goal. So it shouldn't, something's gone horribly wrong if they give you a goal that has not got a heuristic of 0. Remember, you don't get that in Dijkstra, because with Dijkstra it's agnostic of where it's going. It just bumps into the goal. E was 9 and F was 7. So I've written down the H's first. So initially the only thing that goes into the open set is the start node. And that has got a G cost, which is the travel cost, of 0, because we haven't gone anywhere. So we can calculate the F. Now, the way that the algorithm works is we look in the open set for the smallest F cost. So we put the A in straight away. So that's our first selection. The parent of A is nowhere. It's a null. So we can write null or put a dash. I'm going to just put a dash, but you know, you can just put null. Right. Remember, the key bit is now we look at the neighbours. So we look at A and we say, who are the neighbours? And what we're going to do is we're going to calculate the costs for the neighbours. If we've never met them before, this is going to be the first time we do a costing. So they should be blank on the paper. So I've got a neighbour B. So it's cost me nothing to get to A. To travel to B from A is going to cost me 3. Okay, so I put down the cost to get to B is 3. I can then calculate my F cost, which is going to be 8. So that's G plus H. And that was from the A parent. So try and do it logically. Right, so the next one So I tell you what, a lot of people didn't spot C. I don't know why that was. There was people, it was like, why didn't you spot C? Bizarre. Right, so the next one is the C. Now remember, the physical distances don't mean anything. It is just the numbers that we're going. So the cost is going to be 0, the cost from A to C. So that's going to cost me 9. So the F cost for C is going to be 18. And that was from A. The next one was F. So that's at the bottom of my table. Now it doesn't matter whether you did A, B, C, F and you wrote them down as you came across. Whatever system, it doesn't matter as long as the examiner can see this and the progression. So F, again, it's going to cost me the distance plus the cost of A, which was 0. So that's another 3. So in this case, the F cost becomes 10. And that is from A. So that's the end of the phase. What we then do is we go back and we start again and we say, right, have we got to the goal? Have we got anything in the open set? Well, we have actually got 3 items in the open set now. We want the one with the lowest F cost, which turns out to be B. Don't look at the diagram for what you should be picking next. Look at the data. So we're going to pick B and we're going to cross it off. Now it might be that it might be a good idea to put a number to show what order you visited. So I might do that just so I can go back and the examiner can see which order. So I'm just going to put the numbers at the side. Right, so B, we look at the neighbours. It's got a neighbour A, but A's in the closed set, so we can ignore that. Not allowed to re-examine. We've got a neighbour C. C we've already seen. It's in the open set, but we need to see if we can get to C cheaper. So what we do is just say, okay, so it's got C, it's another 3. What did it cost me to get to B? Oh, it only cost me 3. So 3 plus 3, it's only going to cost me 6. That is better than the current cost. So we found a faster route to C. So we're not going to scribble that out, and we're not going to do this. Some people did this, and this was disturbing to me. So some people did this, and then did like that, and you think, I don't actually know what you mean by that. So I would prefer it if you did a nice cross through, so I can still read the number. Right, because I've updated the G cost and found a cheaper route to C, I've got to make sure I update the F cost. So I've got 6 plus 9, which hopefully you can do these sort of numbers, crossing through, so I can still read that was 18, so that was 15. Yeah, I'm going to cut one of these up, aren't I? I know I am. I've just found a better cost, so A is not the best parent, B is a better parent. So I'm showing, and they will look for this in the mark scheme, that you have shown that you have updated your data set. Okay, there is another from B. No, there isn't any more. There's no more neighbours to update. That was the only one. Right, so we're now going to go around the loop again, and we're going to pick the next cheap cost. So looking at it, it looks like it's F. So I'm going to select F. That's number 3. So I'll try this. I never thought to do this before, but let's try it. Right. So we look at F and we say, who are your neighbours? Well, we've got a neighbour A. Ignore, it's in the closed set. We've got a neighbour E. Excellent. Let's have a look. So it's cost me 3 to get to F. To move on to E is going to be a further 8. So that must be 11. Let's calculate the F cost. That's a nice number, 20. So that was from F. If you screw up the parent, you will screw up your root. Okay, so try and do it in that order. There are no other neighbours of F. So we're going to go round and we're going to pick again. So when we look this time, we see C is the cheapest F. So we're going to select F. If you want to write closed above those X's, or put something to describe what that means. X means in closed set or something. So that's my 4th pick. Okay, so neighbours of C. We've got B, but that's in the closed set. We've got A. Well, this is a friendly guy, isn't it, C? We've got A, we've got E, and we've got a new one, D. So let's do the E one first. So the cost to get to C was 6. The cost to get to E from C is a further 3. So 6 plus 3 is 9. That is cheaper than what we've currently costed. So we found a quicker route. So I'm crossing through to get to E. So we can recalculate the F cost, so let's cross that through, but I still want to be able to read it. So I've got 9 plus 9, 18. It's not much quicker, but it is quicker. So F, the previous quick, is now being replaced by C. Right, I've got another neighbour D. And now what some people went, hey, I found the goal. No, you haven't. You're just calculating neighbour costs. We haven't reached it. Until you select it from the open set, you haven't reached your goal. If you do this, you're short-circuiting and you might miss out a cheaper route. If I was to stop now, go, hey, I got to D from C. But we can see I put that massive number there on purpose to force it this way. Okay, very subtle. They will pick numbers that are a bit closer in an actual question to try and catch people doing that. Going, oh, it's obviously that one. Right, so all I'm going to do is go do the calculations for it. I have not selected it yet. Right, so I say, right, to get to C, and don't look at this diagram, look at your data. The cost to get to C was 6. It's a further 13, so 6 and 13, 19. When we calculate F cost, because it's the goal, there is no further cost, so the F is 19. But that was from parent C. Okay, I've got to process my list again now. So I've finished, there are no other neighbours to explore. E is going to be my next one. That's pick 5, because 18 is less than 19. Right, E has got neighbours. F, oh, that's closed. C, which is closed, but it has got D, which is in the open set. But let's see if we've found a quicker route. So to get from E to D is 4. It cost me 9 to get to E. So 4 plus 9 is 13. That is quicker than our previous choice. So we're going to put 13. We're going to recalculate the F cost. So 13 plus 0 is 13. So C isn't our favoured route. We have now got the route from E. Other neighbours, C is in the closed set, so we don't need to process that one. We have not got to the end yet. We've now got to select. There is only one item left, so this isn't a very complex selection. So we select D, so that's pick 6. It's the goal. We can now stop. If we process this properly, we should have now reached the state where we can now trace back and find out what the parental route was. So don't try and draw this forwards, always draw it backwards, and don't do what some of my dozy students in the past have done, is they go starting at D. No, that's where we arrive. So I'm just going to put D at the end, and then I'm going to do an arrow, and I'm going to say, where did D come from? So all I've got to do is look for the parent. You could argue that you could, for this phase of the question, it might be better to have the parent here. I don't know. It's up to you. I prefer it on the end so you don't get confused with all the numbers. Right, so I'm looking for D. So I look along D and I say, where did I come from? E. Then I go, where did E come from? So I look at E. Where did it come from? C. Where did C come from? So I look at C. I don't know why the letters jump up and down as I'm drawing. It's a bit odd. That came from B. Again, I'm not even looking at the graph. We've just scrolled it off the top of the page. Where did B come from? So scroll along. Well, that came from A. You would hope that you get A at some point, since that's where we started. And then where did A come from? Ah, that was the start. I'm going to put route. Right, now what a few people also did is they told me how much it cost. So, yeah, we've got the cost. We've got it's 13. We went, oh, it cost 13. Did the question ask us for the cost? No. Wasting time. Don't give additional information if you're not asked for it. there's nothing wrong with you putting cost 13, but I can look it up from the table anyway, because that's what we just worked out. Okay, and the whole point of it. Right, any questions about the A-star one? It's really important that you do the infinities on the Dijkstra and the cost of naught for the one that you start at, because that's how Dijkstra works. It's agnostic, doesn't know anything. This one's a little bit more intelligent, which is why they'll both find the optimal route. The A-star will find the optimal route if the heuristics are not rubbish. Okay? If the heuristics aren't very good, Dijkstra will find a better route. But A-star will do it quicker because the heuristic gives it that like bloodhound ability. It's like pushing it in the right direction. It's saying, don't favour that, favour this. Okay? Right, I'll stop that record.